Okay, please go ahead, Curtis.
All right, yes, thanks, Steve. And thank you for the nice introduction, and thank you for inviting me. It's nice to be back at least virtually, speaking to Waterloo again. So as Steve mentioned, I did my PhD at Waterloo. Basically, the work I'll be talking about kind of came out of that. And I work in computer-assisted proofs, particularly for combinatorial problems, and particularly problems which can be attacked with the usage of a SAT solver, as I will describe. So let's get into it then. So when I say SAT, what do I mean? SAT is typically capitalized, although it's not actually an acronym. Oddly enough, it's an abbreviation just for satisfiability. So this is a classic problem, right? The satisfiability problem is you're given some logical expression. Here's an example here. So this is read X or Y and not X or not Y. Okay, so this is some logical expression that you can ask, is it true or false? Or can you make it true or false via some assignment to the variables, right? So you can assign X to be true and Y to be false, and it comes back that this is a satisfying assignment to the problem. Okay, so you could, in theory, just use a truth table and exhaustively go over every possible row to solve the problem, but that's too many, right? Because in practice, there's going to be an exponential number of rows, so you can't do that. Okay, but what we have, although we don't have provably fast ways of solving this problem, we have SAT solvers which are basically use trial and error. So you use trial and error to solve the problem, and they can do it freakishly effectively, right? So I started working in SAT around 6 years ago, and I was just astonished when I learned that there are problems which have nothing to do with logic, industrial problems, for example, in hardware and software verification, where the best known way of solving the problem is to reduce it to a SAT problem, right? Absolutely astonishing. And in combinatorics, there's an example I have on the right here, right? So you have, I've colored the integers from 1 to 160 using up to 5 colors, subject to this constraint that if you have a triple of integers, A, B, and A plus B, they're not all colored the same way. So for example, 1 plus 2 equals 3. And if you look at 1, 2, and 3, they're not all colored the same way. Okay, so the question then, this was a famous question, open for 100 years, called the Schur problem. How far can you color the positive integers using, say, 5 colors? So the answer here, this is the best possible coloring. And this was shown, and the only way this has been shown is by a SAT approach, right? You reduce the problem to SAT, and then a SAT solver will come up with a satisfying assignment, which is then translated into a coloring. And it also does the even harder task of proving that this is the best possible coloring, right? You cannot color the integers from 1 to 161 with 5 colors, subject to that constraint, right? That a triple of integers A, B, and A plus B can't be colored the same way. Okay, and so a SAT solver is going to provide a proof of this fact, right? And this is actually going to be important. When you have a SAT result, you can obviously check that. But when you have an unsat result, how do you know if there's no certificate to check? But a SAT solver will actually provide you with a proof that can be checked with a proof verifier. Okay, so not only are they very effective, they're actually very good for certification processes. Okay, so I did work with Steve in the symbolic computation lab here, where Maple was developed, right? Maple is being a computer algebra system that many of you are probably familiar with, right? So computer algebra systems are systems where we'll do mathematics for you. So here's an example. Here's a 10-digit number. Is it prime? You say is prime of this number. To type this command into Maple. Maple will immediately come back true. This is a prime number, and it's not going to just do it. Try every possible trial divisor, right? It's going to actually come up with it has a efficient, clever algorithm for testing primality. This is just one example, right? There's so many functions in computer algebra systems like Maple from many branches of mathematics. One in particular that I want to go over, which will be important later, is take a look at these 2 graphs here, right? On the left, we have a graph with 8 vertices. On the right, a graph with 8 vertices. All the vertices have degree 3. Now the question is, are they actually the same graph? Right? Are they the same up to isomorphism? And you give it to Maple, and what will come back is, yes, indeed, that they are the same graph, right? it's subject to this permutation, right? You have a permutation, you label the vertices on the left, and Maple will provide you with the permutation showing that the graphs are actually the same. Okay, so interestingly, even though the SAT field and the computer algebra field are both have extensive histories dating back, over 50 years, they were kind of operating independently, right? The two communities really weren't sharing the wisdom of the other field. And this is where my research comes in. I started in 2016 as I was the lead developer of this system called MathCheck. And the claim to fame is the very first system that took the wisdom of both the fields, right? We hooked up a SAT solver to a computer algebra system. So I don't know if this is on your end, but okay, wait, there we go. My video feed was flickering in and out. So let me know if there's any trouble with that. Okay.
So we're not having any issues here.
Okay. I don't know why that's, anyways, sorry about that. So we've been using the system called MathCheck in many different universities, right? It's been used now by researchers in Toronto, Windsor, Carleton, Wilfrid Laurier. And as I'll describe in the talk, we've been basically getting orders of magnitude speed up in certain problems, right? So it's a very effective way of harnessing the search power of the SAT solver with the mathematical sophistication of a computer algebra system. So as I'll describe. So I'm going to talk about two main applications, and these are both applications that were published in the last 2 years. One is from combinatorial matrix theory. I'll be talking about a type of matrix known as Williamson matrices. And as a side, actually, there's a relationship to perfect quaternion sequences, which was something we didn't even set out to work on. And then it turns out there's this relationship. We ended up disproving a conjecture in that field, basically by accident. And then the second example I want to talk about is the centuries-old Lamb's problem. Right? So this is a classic problem from finite geometry, and it was kind of high profile. We ended up winning a best paper award for this work last year. So I'll get to that as well. Okay, so first let's talk about Williamson matrices and what are known as Hadamard matrices. So many of you are probably already familiar with this concept, but it's actually easy to define. A Hadamard matrix is a square matrix whose entries are plus or minus 1, and any two rows are mutually orthogonal. Okay, so you can do this computation on your head, right? On the matrix on the right here is a 4x4 Hadamard matrix. You can take any two rows and compute the inner product, right? The ones and the minus ones will cancel off, and you'll get 0, right? And this has to work for any two rows. So these are quite, they're not so easy to find. And in fact, there's lots of open problems. Even with this, it's a nice simple definition. There's lots of problems. We don't even know, given an order, how to find in general a Hadamard matrix of that order. Okay, and so these were studied, I believe, first studied by Sylvester, but they got named after Hadamard, who studied them about 25 years later. That's the way it goes, I guess, when you're naming things. So they have lots of applications, both theoretically and also in practice. Here's a nice slide, a photo I like to show. So this is 3 researchers in the 60s who were working for NASA, because NASA was sending out space probes, right? And they wanted to communicate with the probes, but sending signals over space is going to lead to some corruption, right? So they wanted some error correcting code. Hadamard matrices are nice for that, because if you take the rows of your the Hadamard matrix to be your code words, then the orthogonality is somehow saying that any two rows are maximally disjoint, right? The code words are somehow maximally different, so they can tolerate some errors being introduced into them. Anyways, so you can see how proud they were, right? They framed a copy of the first Hadamard matrix of order 92, and they did this using a computer search, sort of using the techniques that I'll be describing. And actually, if you're eagle-eyed, you can take a look at, oh, my video feed just dropped out again. I don't know why that happens. Anyways, yes, you can see here the Hadamard matrix, one of the ones that we found. This is actually a cross-stitch done by my partner. And so not only are they good for error correcting codes and applications and engineering, they're actually good for mathematical art as well. Okay, so you can see here how it's structured, right? The different colors are there to show you the submatrices which are going to make up this one large Hadamard matrix, right? So you kind of put these submatrices together like Legos, and you get the Hadamard matrix. So this all comes out of a paper written by this mathematician, John Williamson. Amazing paper in 1944. He comes up with this construction, right? And he basically puts these four smaller matrices together in such a way that when you put them together in this nice array, it comes out to a Hadamard matrix. So that was an 8x8 example that he showed, but let me give you the definition of Williamson matrices. Okay, so we're going to be looking for a quadruple of matrices. I've color-coded them A, B, C, D with 4 different colors. Obviously, the entries are going to be plus or minus 1 because they're going to be submatrices of a Hadamard matrix. And then here's the condition that you need. You take the sum of the squares of the matrices and you get a scalar matrix, right? So basically an identity, all the off-diagonal entries are going to be 0. Okay, so ABCD is said to be a set of Williamson matrices. They also have some symmetry properties. So they're going to be symmetric. They're going to be circulant, meaning that every row in your matrix is going to be a cyclic shift to the previous row. And that means the first row, of course, defines the entire matrix, right? So we can consider the first row as a +1, -1 sequence, which, so then you can have a set of Williamson sequences or a set of Williamson matrices, and that's equivalent. Okay, and so here's an example of Williamson matrices of order 5. All right, so Williamson never actually made this conjecture, but it kind of became known as a folklore conjecture. And you can see some of the researchers I showed on the photo there wrote this paper, the American Mathematical Monthly, where they talk about, they expect that Williamson matrices of a given order for any order should exist. Okay, and so this kind of became known as the Williamson conjecture. Williamson himself was a bit more conservative. He doesn't actually make the conjecture, but he says, well, I have the quote at the bottom here, it would be interesting to determine whether the results of this paper are isolated results or particular cases of some general theorem, because Williamson only gave explicit construction in some specific orders. He wasn't able to generalize that to all orders, although mathematicians thought that it should extend because basically the computer searches in the small orders they always found examples. Obviously, that's a bit of not a secure argument, as we'll see. But what Williamson did was he at least found examples in powers of 2 up to 2 to the 5, right? So these are the matrices that he found in his original paper, right? So they're order 4, 8, 16, 32. And so you can look at them and you can, there's not really an obvious pattern here. And actually, it was amazing that Williamson even found these, right? Because remember, this was all before computers. This is 1944. And he doesn't actually explicitly say how he found these, but you can kind of guess. His paper comes up, he proves a bunch of properties about the matrices, and then probably with some trial and error or some guessing, he comes up and he said, oh, well, at least you can do the computations, it works in these cases. But there's no real way to generalize that to larger orders. And so the next open, the next power of 2 would be 64. And this was actually open for 75 years. Basically, the search space is just so enormous, you can't just write a computer program which is going to do the search, right? Just naively, it's going to be too large. And I was kind of obsessed with this problem, right? Because in my when I was at Waterloo, right, I was writing searches for Williamson matrices around order 35, but already I was seeing something's happening here. There's patterns that can be there's patterns here which are unexplained. It's seeming like when the order is divisible by a large power of 2, there's more Williamson matrices in those orders. And we weren't able to search up to order 64 yet, right? And if you had told me back when I was working on this, we'd get to order 64 and 70, I would have laughed at you because it was just totally out of the realm of feasibility, as I'll describe. And yet we actually were able to do it. And we found huge numbers of Williamson matrices of order 64 and many in order 70 as well. So these were the first examples in those orders, and we did an exhaustive search, right? So we found all Williamson matrices in those orders. And what I did then was I sat down, I had all the data, and I started looking for patterns that can be generalized. And I put the general construction that was found on the slide here. I'm not going to go into the details of this, but just to give you the flavor, right? What you do is you basically have a set of seed Williamson sequences, and then you can kind of use those to generate larger Williamson sequences, right? So the construction kind of snowballs, right? The more Williamson sequences you generate, even larger Williamson sequences you can generate. And this is actually, you use this construction recursively, and it proves that Williamson sequences exist in all powers of 2, right? So this is now actually answering Williamson's question that we now know they do exist. So very happy that MathCheck was actually able to lend itself to this sort of experimental mathematics, and now we have a general proof. And so as a side note, as I mentioned, there's actually a relationship between you can equivalently consider a set of Williamson matrices as a perfect sequence over the quaternion group Q8, right? So what's a perfect sequence? A perfect sequence is a sequence which is perfectly uncorrelated with itself. The correlation would be measured by this sum down here. You take this sum, it's basically measuring how correlated the sequence is. If you shift it, you offset it by k entries. Anyway, so if it's perfectly uncorrelated, the sum would be 0. This comes up all the time in signal processing when engineers want to use some kind of like radar system, and they're sending sequences, and they want to synchronize the sequence. You want a sequence which has low correlation with itself, right? So these people have studied these things for a long time. It turns out if you just consider the real or complex entries of Q8, they don't exist, or there's only a finite number of cases which exist. And it was conjectured that also it holds in over the quaternion group. And it turns out, because of this construction, that was incorrect, right? So we disproved this conjecture that we weren't even actually setting out to disprove, which was kind of nice. All right, so that was the punchline. I kind of gave it away at the beginning to get you interested. How did we get there, right? As I said, if you had told me this is where we would have got it, I would have laughed at you. Because back in, let me talk about the state of the art previously. I'll focus on the even orders, because that was where we did the most work. So in 2006, there was a computer algebra approach which found Williamson matrices in every even order up to 22. And then a chapter of my PhD thesis in 2016, we did a satisfiability approach, and this got up to order 30. Now, this is where some eyebrows should be raised, right? Because how are you going to get to order 70 if the SAT solver alone is only getting you up to order 30, right? Because think about this. This is not just like going from 30 to 70. It's not just like doubling the search space or something. You do the back of the envelope calculation. You're increasing the search space by like a factor of 4 every time you increase the order by 1. It's an exponentially sized growing search space. So going from order 30 to 70 is something like increasing the space by 25 orders of magnitude, right? So it just seems like it's totally out of the realm of feasibility. You would never even consider doing it. And yet, so my goal for the rest of the talk is to give you an appreciation of how we did that, right? How is it possible to cut down this enormous search space and actually search it exhaustively? All right, so we're going to go, first I'll talk about the SAT encoding, because we're going to use both technologies, right? The fast search and the mathematical sophistication. So when you're reducing things to SAT, we know SAT is very primitive, right? Because all the variables are either true or false. This is both a blessing and a curse. It means you can only reduce relatively simple things to SAT, but then you're limited in the expressibility. Okay, so what can you do here? Well, in the case of looking for a Williamson matrix, all of the entries are either 1 or -1. So this mapped actually quite nicely onto the Boolean domain, right? You just can define a Boolean variable for every entry in your matrix, and the variable is going to be true if and only if that corresponding entry is 1. Okay, and the variable is false, then the entry is at -1. And so you can do this for your matrix A, then you can do it for B, C, D. You have a set of these variables, and of course you can only do it for the first row because that defines the whole matrix. Then you can, how do you just specify that the set is Williamson? You take the sum of the squares and then you fix that to be 0. So what you can do is you can generate an arithmetic circuit which computes those off-diagonal entries, and specify that they're 0, right? So you have this circuit, and then you can convert the circuit into a SAT formula, right? So I'm not going to go into the details of how you do that. This is all well known, right? You can convert a circuit into a satisfiability instance, right? And then you can give that to the SAT solver. So that's nothing new here, really. This is just using a SAT solver out of the box. Okay, so what would you do? You'd fix your order, you generate the circuit, convert it into SAT, give it to a SAT solver. Now there's multiple possibilities, right? The SAT solver could either return SAT, which would then be a satisfying assignment, which would define the entries in a Williamson set, or you would say the SAT solver would say unsat, and then that would be a proof that the Williamson's conjecture is false, right? It would be a counterexample. Order n would have no Williamson matrices. Or the SAT solver might spin its wheels for it and then just take too long to run, right? This is also happens a lot, right? There's no proof that a SAT solver is going to terminate. It just seems to work relatively well in certain cases. So as I mentioned, we got up to order 30, and then it kind of, the SAT solver started taking too long. And so what you can do in those cases, well, one of the things about SAT solving is that the solver is really not mathematically sophisticated. There's lots of properties that we know about Williamson matrices, which we would like to encode into SAT, but they're just too cumbersome to encode, right? The SAT solver, it doesn't know anything about these properties that the mathematician knows, right? So really, it's really good at doing search in like this. If you just give it a bunch of messy constraints, it can cut down that search space and do the search really quickly, but it's not going to do the high-level mathematical thinking, which is also very effective at cutting down the search space. And so let me give you an example of this. So this is what is known as PSD filtering. And the PSD is a function which is going to be based off the Fourier transform of a sequence. All right, so let's say A is a Williamson sequence of length n. What you do is you take the Fourier transform of that sequence, and then you take the squared magnitude of all of its entries. Okay, this is called PSD A, and this is going to be upper bounded by 4n. Right? This is actually a very restrictive condition. If you just took a random +1 -1 vector, you're more than likely going to get a PSD value over 4n. And you can formalize this and prove that almost all cases you're getting something larger than 4n. Okay, so this is a very powerful restrictive condition that Williamson matrices happen to satisfy. It's basically saying that you can think of this PSD as kind of measuring the amount of periodicity in the vector. We're basically saying they're very constrained, right? The amount of periodicity is very constrained. If you haven't seen the Fourier transform before, it's basically this you compute this sum down here. This is a complex sum. So it's not something that a SAT solver would ever calculate it on its own, or have any, you wouldn't want to give this to a SAT solver in some kind of formulation, right? It just wouldn't know what to do with it. Okay, so it would seem as if then you're kind of constrained to going one way or the other, right? You can either use the SAT solving, just the pure Boolean approach, or you could use the pure computer algebra approach. But we want to use both, right? We want to exploit both the fast search power of the SAT solver and the efficient mathematical routines of the CAS, because yes, the SAT solver alone wouldn't be able to compute the PSD effectively, but with the fast Fourier transform, you can compute it very fast, right? Almost in linear time. So it's going to be, there's mathematical libraries devoted to computing Fourier transforms quickly, right? So what you do is we're going to let the SAT solver execute its search, but also make calls to a computer algebra system to compute those PSD values. So here's how the system's going to work. As the SAT solver is running, it's finding partial solutions. Some variables will be set to true, some variables will be set to false, other variables will be left undefined for now, right? So we have some solution that it's not a complete solution, but at least it satisfies the constraints up to a point. So let's say we have, eventually it's going to come to the point where all the entries in one matrix is defined. So let's say we have the matrix A here, all of its entries are defined. We can give this matrix to the computer algebra system, which again can then call a fast Fourier transform and get the PSD values. The PSD values can then be given back to the SAT solver, and we can compare, is any PSD value larger than 4n? Because if it is, this matrix cannot be a Williamson matrix. And normally this is the case. The matrix can be proven at this point to not be a Williamson matrix. And so here's the cool part. You add that as a new constraint to your problem. Like I said, SAT solvers are great at dealing with messy constraints. You just give them constraints, they're going to be able to know what to do with them to speed up the search, right? So every time we get, we've proven this theorem that the A cannot be a Williamson matrix, we add that as a constraint. And SAT solvers are typically doing this as they're running anyways. Now, if you know anything about logic, the SAT solver is typically based on the resolution rule from logic. It's deriving new facts or new constraints about the search via the resolution rule. But there's no, if something's true, then it's true, right? If we have an oracle like the CAS, it gives us this true fact, we can add it as a new constraint, right? In the same way we'd add something that you learned from resolution. And so you can give a back of the envelope calculation that the running time is going to increase, or the speed up is going to be exponential. The search space decreases by an exponential factor. And this is what we see in practice. This is a graph of the speed up. And by order 44, you're seeing over 1,000 times speed up, right? So order of magnitude speed ups, and it just gets better as you go. And so we would never have gotten up to order 70 were it not for this sort of a technique, right? We called the CAS other ways as well, but this is one of the main techniques which allowed us to scale, right? So we're cutting off exponential amounts of the search space by doing this sort of calling out to the CAS. And so we found a huge number of new Williamson matrices. In the end, it was over 100,000, which was totally surprised us because fewer than 200 had been found by computers. But essentially, it was because of that recursive construction, right? If you have small Williamson matrices, you can kind of combine them together, get larger ones, and then this snowballs. So it turns out if you're searching these orders, which are large powers of 2, you're getting a huge number of Williamson matrices that you don't see if you're just searching the smaller orders. Okay, and so we also disproved the Williamson conjecture. It was already known to be false. There was a search done which showed this counterexample 35. We showed this was the minimal counterexample, the smallest order which Williamson matrices don't exist, and then proposed a new conjecture, which is that Williamson matrices might exist in all even orders. As far, this is still open, and I hope one day that we can resolve this. I hope to live to see that. I don't know if maybe it's true, maybe it's false, but the first open case would be farther than is possible to search right now, right? So it's the kind of thing where you need some new mathematical fact that is going to, you could call the CAS to exploit, right? So maybe one day we'll get there, but for now, this is an open problem. Okay, so let me move on to Lamb's problem. So I love this problem. It has a very interesting history, stretching back all the way to Euclid. So we all know Euclid, right? We've all studied Euclid, the great granddaddy of all mathematicians. And what Euclid did, right, was he defined the postulates or axioms for geometry. So we had 5 postulates. The first 4 postulates were totally simple, easy, concise to state. And then the 5th postulate, the parallel postulate, was more complicated, right? Everyone thought it was true, but it was more complicated than his concise axioms. So this kind of bothered some mathematicians. They would think, okay, well, why not we prove the parallel postulate in terms of the first 4 postulates? And then you have all geometric truths proven by just this nice, simple, concise set of axioms. It would be great. Well, they tried to do this for 2,000 years, right? Many mathematicians struggled with this. And now the answer to this dilemma is well known, right? There's a reason why they were always failing. It's because there's non-Euclidean geometries which the parallel postulate will not hold in. And therefore, there's no way to prove it because there's going to be cases where it's false. Okay, so this was shown in the 1800s. And here on this slide, I've given you 3 examples of that phenomenon. Now, these are going to look strange. They're not going to look probably like geometries you think of out of a Euclid textbook, right? But it's similar to, so there's a finite number of points. It's similar to the case where you have the axioms of a field, and you can consider the real field, infinite number of elements, or you could consider those same axioms, but specify that there's a finite number of elements, right? So that you have the finite fields. Same thing with geometry. You have the axioms of geometry, which has an infinite number of points, but if you specify there's a finite number of points, you can still find models of geometry. And so here's 3 of these cases. These are known as finite projective planes. They have a very simple set of axioms defining them. So you have points and lines. Every pair of points define a unique line. Every pair of lines meet at a unique point, right? So they meet exactly once. And there's the same number of points on any line, right? This will be related to what's known as the order. Okay, so here's the question. Can we do the similar thing that we did for finite fields? We come up with a complete classification of what orders do projective planes exist in. And interestingly enough, in dimensions 3 or greater, you can do that. In dimension 2 exactly, right? The finite projective plane case, this is still open. We don't actually have a complete classification. And here's where Land's problem comes in. The answer is known for orders up to 9. There is no projective plane of order 6. So you can prove this. It comes out of what's known as the Bruck-Reiser theorem. It's going to remove order 6. There can't be a projective plane of order 6. There's other orders it removes as well. It doesn't remove 10, however. And then you can also do a finite field construction. So for any order in which it's a prime power, you can do projective geometry over a finite field, and that will construct a projective plane of that order. There's also a projective plane of order 1, which is actually kind of interesting. Some people think that this actually you're kind of doing projective geometry over some kind of a finite field with one element. There is no finite field with one element, but some people have been thinking there's some kind of phantom field working in the background, or you can actually make sense of this notion of a finite field with one element out of the realm of this talk, but very fascinating stuff. Okay, so let's come to Land's problem now. The projective plane of order 10. Does it exist or not? Now, this was open for many, many years, very famous problem, and nobody could find an example. So it's not a prime power, but that doesn't prove there isn't a projective plane of that order. No one could come up with a reason why it shouldn't exist. So some people thought it would. Lamb here, Lamb is a mathematician at Concordia. He's retired now. Very nice guy. And he was very fascinated with this problem. He wanted to work for, apparently he wanted to work on it for his thesis project, and his PhD supervisor dissuaded him because it was too hard. He came back to it though and solved it with a team of programmers. So this was amazing work. They wrote very, very sophisticated special purpose search code that they ran on a supercomputer for months on end. This was in the 80s, right? It was an amazing piece of work. They got a lot of press for it, front page of New York Times. And their final result was, after the exhaustive search had been done, no projective plane of order 10 was found. Okay, so this is basically the only other case that we know of where the problem has been solved. Okay, now has it been solved though? Because some mathematicians, this is one of the first computer-assisted proofs, and it was a little bit controversial, right? Anyone who's ever used a computer knows the problem, right? Even if the software has been used billions of times every day, very well written, right? It has lots of bugs. It's just a reality, right? Software just has bugs. So the fact that they wrote this code and it ran it a single time, there's nothing that you can really check, right? Even if you have the code, you're not going to be able to verify that there's no bugs. It's just too difficult. And maybe there was administrative error, right? There's nothing that you can check at the end of the day. Either you believe the result or you don't. Obviously, they spent lots of time trying to reduce the possibility of bugs, but they weren't able to say for 100% certainty that this code is actually correct. Okay, so this is where we came into the picture, because what we did, we wanted to kind of put Lamb's problem on a sounder foundation. And this is where the SAT solver's ability to produce unsatisfiability certificates comes into play. What we did is we reduced Lamb's problem to SAT, and then we used the SAT solver to solve the SAT instance and produce an unsatisfiability certificate, which could then be verified. So the takeaway here is that now we're reducing the amount of trust necessary. You do have to trust the encoding, and you do have to trust the proof verifier. But crucially, you're not trusting any search procedure, right? I know from experience, it's very difficult to write a search procedure and make it really, really fast and efficient, but also totally correct. The problem is when you start introducing these efficiencies, you start introducing bugs. Okay, and so the SAT solver itself is basically a search procedure, which is quite sophisticated, right? SAT solvers do have bugs, but we're not trusting the SAT solver at the end of the day because we have the certificate, which is tested by a proof verifier. And the proof verifier is much simpler, right? It's just testing, does this line follow from this line, follow from this line, just like using the resolution rule. Okay, so that's where we're going. As I mentioned, we do have to trust the encoding. So but it's not actually not that difficult. I summarize it on the slide right here. So the idea is to define, you can come up with a Boolean representation of a projective plane, right? So you're going to have the set of all possible incidences of all possible points and all possible lines. So the rows of this matrix are going to be the lines of the plane, and then the columns represent the points of the plane. And if you have a 1 in the ijth entry, then the ith line is going to contain the jth point. Okay, and then you have the axioms of a projective plane. They're going to specify that there's the same number of 1s in every row and in every column, right? So in order 2, there's 3 1s in every row and there's 3 1s in every column. And then there's also going to be this restriction that the matrix contains no quads. A quad would be a rectangular submatrix with 1s in the corners. And so you can visually inspect each of these matrices and then convince yourself there are no quads. A quad would correspond to 2 points lying on the same 2 lines, which would be a no-no in projective geometry, right? Any 2 lines could meet at exactly 1 point. Okay, so you can reduce all these things to Boolean logic. You can give it to the SAT solver. The SAT solver is not going to solve it. Like I said, right, it's going to be spinning its wheels because it's not exploiting the mathematics. It has no knowledge of what a projective plane is. You're just giving it a bunch of constraints, which then it tries to make sense of. So now let me just give you a sense of the mathematics behind the problem. This is absolutely beautiful mathematics. The way it just works out is gorgeous. And it's based on coding theory. So what you do is you take this hypothetical projective plane of order 10. So say it exists. You're going to have 111 by 111 binary matrix. You can take the row space of that matrix modulo 2. Right? You take the row space of this huge matrix over GF2, and you get a set of binary vectors. All right? The weight of a binary vector is going to be the number of 1s in it. Here's the cool part. So based on these things called the McWilliam identities, you can analyze the weight distribution of the code. That is the number of vectors of a given weight in this hypothetical code. We don't even know if it exists, but if it does exist, you can prove that there must exist vectors of weights either 15, 16, or 19 in this code. Absolutely phenomenal. It's amazing. And it's great for the search as well, because this gives you a lot of information. You can then break the search into basically 3 cases. Assume a vector of weight 15 exists, and then generate a SAT instance based on that. Assume a vector of weight 16 exists, generate a SAT instance, and then same thing for 19. And this dramatically reduces this size of the search. Okay, so still, this is what Lamb did. Basically, they predicated their search based on this machinery. You can give this to the SAT solver, but still it needs help. Still, there are mathematical constraints which are not so easy to encode. And the issue is basically symmetry. The way that you define a projective plane, you're not really specifying any distinguished points or lines. And if you think of that big 0, 1 matrix, you can permute any of the rows freely. You can permute any of the columns freely. You just get another projective plane, which is essentially the same thing, right? It's the same up to isomorphism, but it's going to be different as a 0, 1 matrix. This is a big problem from the SAT point of view, because SAT solvers has no knowledge of isomorphisms or any mathematics like this, right? It's going to consider these 2 matrices as 2 different solutions. It's basically going to be repeating the search space, the search many times over in this different guises, right? So whenever there's a symmetry that exists in the space, you want to limit it. It's called symmetry breaking. So what you could do, one thing to do is to fix an ordering on, you can like sort the rows, sort the columns, and that removes a lot of symmetry. It still doesn't remove it all, though. There's still these lots of non-trivial symmetries which are going to exist in the search space, which the SAT solver does no knowledge of, right? It's going to dramatically slow down the search, because for every symmetry that exists, you're just going to recreate the same search over again. And so here's what we do. We want to do symmetry breaking. And we know that a computer algebra system is really good at detecting these isomorphisms or symmetries, right? So here's how it works. As the SAT solver is going to be, as I mentioned, right, it's doing its search, it's finding partial solutions, right? So it's going to be a complete definition for all of the points and lines up to some point. Here's just one I give it on the slide as an example, right? You have 4 points here and 6 lines. And you can give this to the CAS. The CAS can analyze it and compute its isomorphism class, right? Or a certificate, which is going to uniquely determine the isomorphism class that this object exists in. And so you record, every time you see an object, a partial object, you get the isomorphism certificate from the CAS and record it. And then if you ever have a duplicate, right, you see the same certificate again, but the object has changed. Well, now you know this new object, you want to block it, right? You don't want to consider it anymore because you already considered the exact same object. Like imagine you rotated this thing 180 degrees, you get something which looks the same, but it's actually, to the human, it looks the same, but to the SAT solver, it looks different. But we block it because we don't need to consider it again, right? We only care about projective planes up to isomorphism, right? So this is dramatically going to speed up the search when there's a lot of symmetries which exist in this search. All right, and so the numbers bear that out. So we solved each case in sequence, 15, 16, 19. 15 ran is really quick. It's 5 minutes with the SAT solver without the symmetry breaking. It's like a couple seconds with the symmetry breaking though, so order of magnitudes speedups there. There's many CAS approaches in the literature which we compared to. They ran within 3 minutes, some ran over an hour using different CASs. The weight 16 search is much more difficult. The CAS approach ran in 16,000 hours. We were able to solve it in 30 hours just on one desktop. And that was because we were able to dramatically exploit the symmetry breaking, right, by making these calls. The weight 19 search was more comparable. In this case, most of the search is not symmetric, so we're not seeing these asymptotic or order of magnitude speedups. Although in the very first component of that search, there is a lot of symmetry which exists. So the very first thing you want to do is search for all possibilities of the first 19 points. And in that case, I think there's like 50 million possibilities for that submatrix. And there's lots of symmetries in that. And it turns out to speed up the search by a factor of 150 if you make the call to the CAS. There is going to be some overhead for doing that, right? There's overhead because you're making these isomorphism certificate calls. So you do pay the cost for that, but it's far and away worth it to do that, right? 150 times faster. Okay, so I mentioned that LAM's original search could not be totally certified to be bug-free. More than likely, there's some kind of bug. And in fact, now we know that there must have been some kind of a bug because what LAM did was they published their intermediate results, and then we can verify those intermediate results. Also, there was an independent verification done in 2011, which did the same thing. They duplicated LAM search, but they produced intermediate results, which we could check. And so one thing that we noticed, in most cases, the intermediate results we matched with what the SAT solver was giving us, but in some cases there was discrepancies. So in one case, I've drawn it on the right here. This is a partial projective plane of order 10, and it has 111 rows, it has 51 columns. Okay, so it doesn't extend to a full projective plane because it doesn't exist, but this partial projective plane was asserted not to exist in the previous search. So the previous search was predicated on the fact that this doesn't exist. And so obviously there was some kind of a mistake where they overlooked some part of the search because, as we can see, it does exist, right? And you can check that all of the axioms are satisfied, right? There's no quads in the matrix. There's 11 ones in every column, and there's up to column 51, everything's satisfied. It doesn't extend, but they said that this shouldn't exist, and it does. So there was some kind of an issue. And similarly with LAM search, there was intermediate results which were inconsistent with the results of MathCheck. Okay, so I don't have time to go over every possible problem that we've solved, but this is just kind of the high-level summary. If you are interested, check out the website. And you can see here, so it's interesting, the different CAS functionalities that you have. A lot of Fourier transforms are useful, graph isomorphism, traveling salesman solving. Basically, the type of problems that you want to attack are problems which have some kind of Booleanizable flavor, right? So they have something which can be translated into SAT, at least in some component, right? Like the graph problems, for example, right? Every edge in a graph can either be there or not, right? So that can be a Boolean variable, which is on or off. And matrix problems where the entries are 0 or 1, or sequence problems, things of that nature where you can reduce a significant component to SAT, but then there's some other mathematical structure of the problem which the SAT solver won't have any access to, right? So the SAT solver is going to be great at doing the search with learning, but there's something which it's going to be missing, which we want to like feed into it via this oracle. And so, as I mentioned, this is kind of a budding new field of computer science, right? There's kind of a whole community that's just kind of grown up around taking the techniques and wisdom from the SAT community and the computer algebra community and kind of combining them, and then getting these impressive results on different problems. For example, I have 2 citations at the bottom of work that would use this approach to find small circuits for matrix multiplication, a classic problem where we still don't have the best. There's no, even for 3x3 matrix multiplication, we still don't know the optimal algorithm for multiplying 3x3 matrices. But they found a bunch of new ones using this sort of approach. And for verifying arithmetic circuits, again, it's a very difficult problem, which they were seeing really good speedups where they combine the SAT solver to the computer algebra system. Okay, so just one slide on conclusion here. I hope I've convinced you that searches that were previously out of reach have now become feasible because of this sort of techniques, right? So the exciting thing is that there's a lot of low-hanging fruit here, right? Because only in the last several years have we had the technology to put these 2 technologies together. So what I've been doing for the last 5 years is basically jumping from problem to problem. I have my hammer, right? And the saying goes, I use it on each problem in sequence, and it turns out, we're getting these speedups where we could only dream of in the past, right? If you're only going to use SAT technology itself or only CAS technology itself, it doesn't scale as well as if you can use them both, right? So I've just kind of been going from problem to problem, and seeing how it works. And it's not something that just works out of the box, but with some you're trying different encodings, trying different CAS functionalities, you end up with these nice results. And so one of the reasons why I was happy that Steve reached out was I think Waterloo is a perfect place to sort of do this sort of research, right? So I'm hoping people in the audience have problems maybe in your own research, right? Where you're thinking, this sort of technology might actually be beneficial, right? We can actually push the state of the art farther than could have been done previously, because now we have tools that will allow us to do that. So if that is the case, please reach out. We're happy to work on, putting the technology of MathCheck towards your own research area. Last thing I'll say is we are also hiring research assistants to continue this work on MathCheck to many different domains, right? Like I said, there's too many for me to do just myself. So we're kind of delegating it to other people, and seeing how far we can push it in all different types of domains. Anyways, I will stop there, and thank you everyone for your time, and I'm happy to answer any questions now.
Okay, let's thank Curtis for a really interesting talk. Questions?
Douglas, I think I see, or no, that's a.
Okay, so I have a few questions. So in terms of the practical aspects, do you use Maple for the CAS side, or do you use like purposely built C code, or?
Yeah, so that depends on the problem. Sometimes you just call the CAS directly, right? So I think the traveling salesman example did that. And then some other times we're calling mathematical libraries. So for the Fourier transform, the sort of this de facto standard is FFGW. For graph isomorphism, you can use Naughty for example, as one of the big graph isomorphism libraries. So it really depends on the problem and how efficient, where the bottlenecks are. Sometimes you can just use the sort of a maple or implementation, or sometimes you have to like kind of write your own C code for that component.
And for, I don't know, one of the problems you talked about today, how often is it calling the CAS? Like in terms of the total computation time, how much is spent in the CAS versus the SAT part?
That varies. I think in the Williamson example, it was something like 20% of the time was doing the Fourier transforms. So it's normally, a significant component, but it's, like I said, it's far and away, if you have the right, learning the right thing, it'll totally, you don't even have to worry about the, because you're seeing orders of magnitude speed up anyways.
Other questions?
Okay, there's some people in the chat I see.
David or Ashwin, you're both, either one of you can go.
Yeah, hi. Actually, I was wondering if you have an explicit description of the perfect sequences that you found.
A description of them?
Like an analytic, like a formulaic description?
Yeah, so if you check the paper, it was in the transaction of information theory, and it's an explicit construction, right? So to extract a construction, you can actually generate these things as far as you want.
I'm actually looking at your paper right now.
Can you tell them the page number?
Maybe I'll ask you this question offline. Maybe I should really take a closer look.
Yeah.
The reason I'm asking is that there's a connection to a problem in quantum communication as it happens, and there's earlier work by that you cite in your paper that we've been using, and it's good to see that there's this progress that you've made. And
yeah, I like
implications for this problem we've been working on.
Yeah, I'm happy to talk about that. Like I said, it was kind of something we just fell into, right? We didn't set out to do this, and it turned out there's this relationship, and it worked out nicely.
Okay, there was another question.
Yes, I had a question. I just, first of all, thank you so much for a really incredible talk. And I was wondering about actually the picture behind you. It looks suspiciously like some of the other ones. I was wondering, is there a story behind that matrix?
This one in particular.
Yeah.
So this is a 160. So it's a Williamson matrices of order 40. And so you put them together, you get a Hadamard matrix of order 160. Do you mean about the actual art piece, or just the?
Either one, yeah.
So it was done by my partner, who was learning how to cross stitch, and she saw the framed copy of the Hadamard matrix from the NASA press release, and she's like, well, wait a minute, I can cross stitch that, right? So it basically that's what she did. It took her like 6 months or something, because there's I think there's 12,800 stitches if you calculate the number of ones in the matrix. We ended up submitting it to the Maple Art Gallery, where it got the judge's choice. So we're happy that, like you said, it's very visually stunning. There wasn't anything particularly special about this. We didn't want to do the Williamson matrix of order 70, because it would have been, taken her over 2 years or something. But this is kind of the new ones that we found.
Very cool. Thank you.
Thank you. Yeah.
Okay, if there's nothing else, let's thank Curtis again for a great talk. Okay, I'm just going to stop the recording.